In this video, we're going to continue looking at the concept of a limit, but we're going to use a slightly different approach. Well, what is that approach? Well, I have it here in the title of this video. We're going to look at limits, but look at them graphically, right? If you looked at the previous video, we actually used what was referred to as a numerical approach, where we were using a table with lots of values and we were looking for certain patterns. Now we're going to be looking for those patterns from the graph of a function and see if we can use that graph to illustrate some of the same concepts that we saw earlier, right? Now, in order to do that, let's I'm going to consider, let's consider this function, and I'm going to pick a piecewise function. And you might remember these from algebra, and I think this example, not only will it help with the concept of the limit, but it will help you to remember how to interpret and to make sense of piecewise functions, right? So let me write down the function, and then we will look at, okay, how do we graph this and so forth. So let's say this is my function, right? So that's my piecewise function, and we're going to try to figure out how to graph this. Now, a piecewise function basically is referring to a single function that is defined differently for different values in their domain, right? So when you look at these two pieces, if you will, it's almost like you don't want to think of this as two functions, right? But it's made up of two pieces. The first piece, this is simply y equals x. And then this piece is simply the quadratic y equals 3 minus the quantity x minus 2 squared, right? Now, if I were to ask you to sketch this function y equals x by itself, you would probably come up with a graph that looks like this. Right? Y equals x. It's a line that passes through the origin with slope +1. This is a quadratic. We know it's a quadratic because we can see this binomial being squared, but it's not written in the ax squared plus bx plus c standard form. It's actually written in terms of the vertex form, where you can identify what the vertex of the parabola is, right? And if you look at this, right, and that's an important thing, and I encourage you to maybe go back. Hopefully you have your notes from algebra, where you can look at quadratics and look at different forms that they can take and how the different forms will enable you to come up with a graph quite easily. So, but just to help you see the connection between this equation and the sketch that I'm going to draw in a second, notice there's several ways you can write this, right? So you could certainly write it like that. It's the same expression, and what we've used here is the commutative property of addition, right? And the fact that there's a negative sign in front of this, so this term right here is a perfect square. And since there's a negative sign in front of it, what it means is that this parabola has to open downwards. So it has to look like this, right? And then the fact that it's, again, in that where this term is a perfect square and then we have this constant right here, what it means is it's basically a parabola, this perfect square that has been shifted up 3 units, right? So, you know, if the +3 wasn't there, the graph would be like this, and it would be right at 2, right? So this what I've drawn here is the graph of y equals negative x minus 2 squared. If I add the plus 3 now, it's going to shift the graph up 3 units, right? So this plus 3, adding a constant to, you can call it like a base or a parent function, is going to shift. If we add a positive constant, it's going to shift that parent function upwards that many units, right? So what does that mean? Well, the graph of this piece, if we were to graph it in its entirety, will look something like this. So I'm not going to find like the intercepts or anything. All I'm going to do is just, we know that the axis here, so the line of symmetry would be x equals 2, and then we'll have to move it up 3 units, so roughly there. So this is 3, this is 2, and then it has that kind of general parabolic shape like that, basically, right? Okay, so again, if you think of these two pieces as two separate functions, this would be your linear function, this would be your quadratic function, but that's, we can't draw both of these and say, hey, this is the graph of f of x. What we have to do is draw the graph of the line for values of x that are strictly less than 2, right? It would be linear. And then for values of x that are greater than or equal to 2, it would be quadratic. So let's see if we can sketch it. I'll switch back to white here and see if we can come up with a sketch. All right, so at x equals 2, something happens, right? This f of x switches from the linear function to the parabola. So I'm gonna mark off x equals 2. But before 2, so for all values of x less than 2, you just draw the linear function. So it will be something like that. And now, since the inequality is strict, in other words, the equal sign is not on the less than, it doesn't fill in right at 2. So there should be like an open circle right there at x equals 2 because of this strict inequality, right? Then what does the rest of it look like? Well, as soon as you actually hit x equals 2, then it switches over to the parabola. And what do we know? At x equals 2, the parabola has a value of 3, and then it goes down in that nice parabolic arc. So now the question is this 3 or is 3 somewhere else? Well, how would we know? Well, this linear function is y equals x. If there was an equal sign on this inequality, then it would be shaded in here, and when x equals 2, your y value on the line would also be 2. So I know that the open circle corresponds to y equals 2, right? So that means the parabola starts, like 1 unit above that at 3. And then I have to ask myself, do I shade it in here as I start to draw the parabola? And the answer is yes, because the equal sign is right here, right? So looks like this. And then I have my parabola, and then it goes down. So let me just say that things continue this way. Yep. So this is just a very rough sketch of the graph of this piecewise function, y equals f of x. All right. So that in itself is an important skill. And now what we want to be able to do is to use this to talk about the concept of a limit. So let me bring this down a bit, right? Now, let's ask ourselves a couple questions, and just like we did in a couple of previous videos. So here's my first question. What is the value of this function at x equals 2, right? So what is the function value here, right? Well, basically the way we would evaluate or to figure out a function value is we would take the value of x and plug it in. But what do we do when the function is piecewise? Well, we have to do an extra step. That's where these inequalities come in. These inequalities will tell us what piece of the function to use for each x that we plug in. So in this case, we're plugging in x equals 2. So you have to ask yourself, is 2 less than 2? And no, it's not, right? 2 can't be less than itself. Is 2 greater than or equal to 2? And yes, it is. So because the value of x that I'm plugging in satisfies this inequality, I would have to use this piece of the function. And that's another reason why the circle is shaded in here. So the point is actually here. It's not here, right? So we got open, closed. Same thing we used, the same words we use for inequalities. Open inequality, closed inequality. So to figure out the function value at x equals 2, we would have to evaluate the bottom piece of the function. So I'd have to plug 2 right here. So it's going to be 3 minus the quantity, 2 minus 2, that quantity squared. Well, just doing a little bit of algebra, what do we get here? We end up getting 3 minus 0 squared, using our order of operations, and then that's just 3, right? So that is the function value as x equals 2, right? So now let's ask this other question. In fact, let's ask a few questions about limits now using our limit notation. So let's ask this question. What is the limit as x approaches 2, but let's use that little minus sign, and then of f of x, right? So what is that? Well, remember what this symbol means. It means we want x to get closer and closer to 2, but only from the left, right? So we can only use values of x that are less than 2. So that would correspond to here, right? You're getting closer and closer to 2. You're not plugging in 2, you're plugging in values like 1.9, 1.99, and so forth, right? But we don't need to plug the values in. The information is there in the graph. We just have to interpret this, right? So then we have to ask ourselves, when x is kind of moving along this blue arrow, then think of what part of the curve you would be on. Like this value of x would correspond to this value of y. And then as x increases and gets closer and closer to 2, but it doesn't go beyond 2, then I would essentially be tracing out this part of the graph. And then what I would have to look at is say, well, what are the y values on this portion of the graph approaching? Well, they are getting closer and closer and closer to 2. They never quite get there because of the way the function is defined, and we have that open circle. But as x gets closer and closer to 2 from the left, y gets closer and closer to 2. I guess you could say from below, right? But the idea is As x goes this way, y goes this way. So what is the y value, right? So the limit from the left in this case would be, or is, 2, right? And this is an important thing because we're not looking at where the open circle is. We're looking to see what, if we were to continue getting closer and closer to x equals 2, where would this portion of the graph get closer and closer to, right? And the y value here is 2. So this is the one-sided limit from the left, right? Well, that's what happens from the right. So let's answer this other question. So what is the limit as x approaches 2, and now let's make it plus, of f of x, right? Well, 2 plus, that means you are bigger than 2, but then you're getting closer and closer to 2. So let's say you start here, and then you're getting closer and closer to 2. So these would be the values of x. And notice I'm making sure that my arrow doesn't touch the little hash mark there, because we're not going to actually plug 2 in. We're just going to plug values of x that are bigger than, but close to 2. So then what value, so what y values would correspond to these x values? Well, let's say this x would roughly correspond to that y. And then as I, in this case, decrease my x values, as I make them get closer and closer to 2, I would be tracing out this portion of the graph. And then I'm going to have to ask myself, again, I'm going to make sure that my little arrow doesn't touch the circle there. But then I can look at the pattern on the graph here and ask myself, what value of y is the graph getting closer and closer to? And it seems like it's getting closer and closer to that closed-in circle, which we know corresponds to a value of 3. Right? So that is the value of this one-sided limit from the right. So this is 3, right? And this is an interesting and important kind of property that a lot of these piecewise functions have, in that from one direction, right? In this case, from the left, the function approaches a value of 2. But yet in the opposite direction, or other direction, in this case from the right, the function approaches a value of 3. So what do we say? So the one-sided limits, they're okay. This one-sided limit is 2. This one-sided limit is 3. But what do we say about the two-sided limit? So what is the limit as x approaches 2? What if we try to answer the question about the two-sided limit? Well, because these two numbers are different, it's like the function is not approaching the same value from both sides. So in this case, what we say is the two-sided limit is undefined, right? So this is undefined. Right. In fact, what I'm going to state now is a theorem, and it's not a theorem that we can prove in this course because it uses a little bit more rigor than what we're introducing for limits. But let me state this theorem. And so I'll basically say this. So the limit, let me write it like this. I'll just write it completely symbolically. If the limit as x approaches a number from the right of a function is also equal to the limit as x approaches that number from the left, right? If the limit of this function from the left is the same as the limit of this function from the right, And so let's just let's just give it a symbol L, right? If this is the case, then what we can say is that the two-sided limit has to be the same, right? So we can drop the plus or minus here, do this, and then that's equal to L, right? So this is basically saying that, in fact, let me take off the if part of it, right? If the one-sided limits are equal, right, then the two-sided limit has to be equal to that value. Similarly, if the two-sided limit exists and is equal to a certain number, then the one-sided limits also have to be equal to that number, right? And this just kind of formalizes what we saw in a previous video, that in order for us to conclude that the two-sided limit exists, both one-sided limits would have to be equal to the same number. If they don't equal the same number, then we would say that the two-sided limit is undefined, and that's what we saw in our piecewise example here, right? Now, let me before we wrap this video up, let me just do some like what if scenario. So these are like what ifs, and you should always ask yourself, well, what if something changes? So what if? And so the first what if I'm going to ask is, what if the function looked like this instead? In fact, let me remind you of what the original function is, right? So there is that piecewise function. Let me change one thing here, right? I'm going to change one thing, and we're going to see how it affects our answers, right? So if I did the x when x is less than 2, and then if I do the 3 minus, and then the quantity x minus 2 squared when x is greater than, but let me not put the equal sign there, right? So what if the function looked like this, and this is fine, right? So we know that when x is strictly less than 2, it's the linear function. When x is strictly greater than 2, it's the parabola. But what happens at 2? Well, what it means is that this function is not defined at x equals 2. So the graph would look like this. You would have open circles at both ends like this, right? And what we would say is, so let's kind of go through the different possibilities here. So I could say that f of 2, now there is no y value that corresponds to x equals 2. Because if I asked you to plug 2 in, you couldn't plug it into either piece, right? You couldn't plug it into this piece because 2 is not less than 2. You couldn't plug it into the bottom piece because 2 is not greater than 2. So this is now undefined, right? So this, or let's just say, does not exist, right? But the one-sided limits are the same, right? You know, we're still approaching the value of 2 there. We're still approaching the value of 3 there. So the one-sided limit as x approaches 2 from the left of this function is still 2. The one-sided limit from the right of this function is still 3, and the two-sided limit still is undefined, right? So the limit or does not exist. Now, sometimes you can make a distinction between does not exist and undefined. I don't do that at this level. So what you could also say that this does not exist, So I'll go ahead and do that just to show you that it's okay to do that. Right? So you can see by taking away the equal sign that was here, it affects the function value. It doesn't affect any of the one-sided limits, and it doesn't affect the two-sided limit. All right? One more what if. And so again, I'm going to change one piece of this function, but now instead of messing with the domain, I'm going to change the linear part, and I am going to do this. I'm going to put a +1 there, and then I'll keep everything exactly the same. And then we're going to say, well, how does it affect, again, these things, right? Because these are the types of questions that you will have in your initial coursework, right? You're going to be asked about function values and limits and so forth, particularly of these piecewise functions. So if I have a +1 here, remember what happens when you add a constant to like a parent function or a base function. It shifts the graph up, and in this case it's going to shift it up by 1 unit. So instead of the linear function getting closer and closer to 2, the linear function is now going to also get closer and closer to 3. So this is what it would look like. You would have the linear function, and there is its whole. And its whole would correspond to or coincide with the hole on the parabola. So then the parabola, it would just come down like this. And then you wouldn't have this this kind of jump or gap between the two pieces. And we would know that now this is 3. So how does that affect our answers? Well, because I still took away the equal sign, I could say that f of 2 still does not, or actually, yeah, my grammar here was terrible. This should be f of 2 does not exist. And then in this case, f of 2 also does not exist. And I need to fix the limit as well. There we go. So the function value does not exist, but now look at the two-sided, or let's start with the one-sided limit. From the left, the linear part is approaching 3, and the parabolic part is approaching 3 as well. So now we can say that the limit from the left is exactly the same as the limit from the right. So I would have they would both be equal to 3, right? So this changes, and then that also affects the bottom, our two-sided limits. Our last conclusion is that the limit as x approaches 2, the two-sided limit of this function, is also equal to 3, because now the two one-sided limits are the same value, right? So again, these, I think it's important to see. I mean, we could go through lots of different types of functions, but the reason why I am changing one function slightly to show you the subtle differences between function values and one-sided limits and two-sided limits, and how every little aspect of the function is important. So you can't overlook certain things, right? So hopefully, this is again giving you another way of looking at limits, and this is kind of the graphical approach. It's very visual. You just have to know how to read the information from that graph.